So welcome to our algebraic graph theory seminar this week. And today Anna Schilling is going to talk about dimension formula of generalized splines of degree 2.
Yeah, thank you so much for the invitation to speak in your seminar. I should say that usually I work in sort of algebraic representation theory, in particular crystal graphs and things like this, which are actually about like representations of quantum algebras. But today I'm planning to talk about some recent work I've done with Shaheen Nazir and Juliana Tymoczko on splines. So this is a slightly different topic from what I usually talk about, but I thought it would fit very well with the topic of this seminar. Okay, so first, let me tell you what is a spline. And actually, our definition of spline is slightly different from sort of the classical definition. So I need to make sure we are sort of on the same page. So what we are going to do is we are going to fix a commutative ring R and a finite graph G. So V is the vertex set of the graph and E is the edge set. And we are always going to look at edge labelings of the graph. So to every edge in the graph, we are going to associate an element in this ring that we specify. And I should say the ring that we are mostly interested in this talk is just the polynomial ring over two variables, x and y, but this will come up later. But in principle, you can define it for any ring. And then a spline on this edge labeled graph is basically an element where you pick an element in the ring for every vertex of the ring. So it's an R to the V. And it should satisfy certain conditions, namely if you take two vertices that are adjacent, that they're connected by an edge, if you take the difference between the labels on the two vertices, this should be a multiple of the edge label. So alpha UV would be the edge label that you associated to this edge. Okay, and by multiple I mean over the ring. Okay, so that's our definition. And so the collection of all splines, they form a ring. And you can also think of it as an R module if you do vertex-wise addition, multiplication, and scaling. Okay, so here's an example of a spline. So here's a super easy graph. I mean, just basically a line. It has three vertices and two edges, right? So it's just a line. And then I have to pick a labeling for the edges. I have two edges in this case. And as I said before, I'm actually working over the polynomial ring in two variables, x and y. And here now I have just picked x for the first edge and y for the second edge, right? So that's just an edge labeled graph. And now we want to label the vertices. So if we want to get a spline, we now want to label the vertices such that the difference between two adjacent vertices is a multiple of the edge label. Okay, so for example, I could pick for my first vertex just the number 3. So if we are, let's say we are working over C, the complex numbers x, y, I can pick 3. And then, well, what can we do for the next vertex? Well, the difference between the label of this vertex and that vertex has to be a multiple of x. So as you can see, if you take the difference, the 3 cancels out and I get 2x. Which is a multiple of x. So this would be a valid labeling. And then for the last one, I need that if I take the edge label for this one and I subtract the edge label for that one, it should be a multiple of y. And you can see that the difference is y squared, which over the ring R that I specified, it is a multiple of y. So this would be a spline for this particular edge labeled graph. Okay, and for this particular example, let's see whether we can actually write down a basis for the splines. And here would be a basis. So one of the basis elements you could pick as the constant spline. So I just put 1, 1, 1. right? That would be the constant spline. And then since now sort of you can always get something on this first vertex, for the other basis elements, I can pick 0 there. And then remember the difference between this element and that element has to be a multiple of x. So if I just make this x, then this would be, and then this is also x, so the difference of those two is 0. This you could pick as a basis element, and then if we do the same sort of for the last one, we pick 0 for the vertices that we've already picked, and then y for the last one. This would actually give us a basis. And I hope that this example sort of shows you that if we actually pick a tree, any sort of tree, you could sort of play the same game. You could pick one of the vertices as the root, then you could make just the constant spline, and for the other basis elements, you would put 0 at the root, and then you would just sort of go to another vertex, and whatever that edge label is, you would put that label on everything else sort of above the root, away from the root on those vertices. Okay, so for trees, it's relatively easy to write down a basis. And then, of course, you would also know what the dimension is, because once you have a basis, you would know what the dimension is. And I mentioned before, so that this definition that I just gave you of splines is sort of, in some sense, actually dual to what people usually call splines. So if you, for example, look on Wikipedia, splines are actually used in approximation theory. So here, for example, we have the surface of a car. And what people would like to do is sort of approximate the surface by some polynomial surfaces, or surfaces that are specified by polynomials. And you want to do it in such a way that sort of they piece together nicely. So it's some sort of approximation, piecewise approximation of the surface. Okay, and our definition is sort of dual in an algebraic sense. So if you view that previous element sort of as a graph, then the graph that we would be looking at would be the dual of that graph. Okay, and the definition that we are using is more in line with GKM theory. So this is some theory that comes from equivariant cohomology, so it has more like an algebraic background. And for that, you usually fix a variety x, and you have some torus action, and then the torus fixed points, and the one-dimensional T orbits form a graph. And then the cohomology of this corresponds to the splines in some way that I defined before. So this gives you some graph with some edge labels that satisfy these conditions, that if you take the difference between two adjacent vertices, it will be a multiple of the edge labels. Okay, so what is the problem that I want to actually address today in this talk? So there's something called the upper bound conjecture for splines, and this conjecture asks for a dimension formula for splines of degree at most d. So this degree really means like the degree of the polynomials that we are interested in, right? So because we are mostly working over a polynomial ring. And then smoothness R. So the smoothness you can think of like we wanted to piece together these polynomials, and they should fit together in some way. And the smoothness tells you up to which derivative they should sort of fit together. And in this classical setting, people usually look at triangulated regions in the plane. And a dimension formula for planar triangulations of smoothness 1 was proven for dimension greater or equal to 4 by Alfeld, Schumacher, and Hong. And it was conjectured by Strang for the degree equal to d, and proven in the generic case by Bellera, but the problem is wide open for degree 2. So what I want to do today in this talk is I want to study this degree 2 case in more detail. And as we will see, there's actually a lot of graph theory or combinatorics related to graph theory that comes into studying the problem for d is equal to 2. Okay, so that's sort of the problem. So d is 2 means the degree of our polynomials is 2. And so if you sort of unravel all the definitions, smoothness 1 really means that in the dual graph, so the setting that we are interested in, the edge labels would be by degree 2 polynomials of the form ax plus by plus c squared. Okay, and so this sort of corresponds to the edge in the original triangulation being on the line ax plus by plus c equal to 0. And it turns out that if you sort of align your things in a proper way, you can actually get rid of this constant term c. So we are actually going to assume that in this talk that our edge labels are all of the form ax plus by squared. And furthermore, you can actually also assume that the coefficient of the x is equal to 1. You can always sort of arrange it in such a way. So I will actually be mostly just talking about edge labels of the form x plus some constant y squared. Okay, so that those are the labels for our edges. And so we don't make a lot of assumptions on the graph. So for example, we don't actually require that it's dual of a triangulation. So the degree of the vertices can be more than 3, for example. But later in the talk, you will see that in some cases, to make certain statements, we will actually have some conditions on the graph, but I will state them when I get there. Okay, but for right now, we are just going to assume that the graph is a finite planar graph, and we usually work with a planar embedding of the graph. Okay, and so as I mentioned before, we want to know a dimension formula for splines of degree 2. And in what I'm going to talk about, we usually always sort of take out the constant spline. So when I talk about the dimension, it will probably differ by 1 from what it should be, because I always sort of assume that it's not the constant spline. Okay, but let's go back to the example that we had before, right? So here we had a very simple graph, and we saw that this was a basis for the splines of this edge-labeled graph. And as I mentioned before, so for trees, you can sort of immediately generalize this, and you can get a very easy formula for the dimension of the splines. But it becomes more complicated when we have loops in the graph. And let me just briefly explain why and how we then capture these conditions that arise when we have loops. So here's a very simple sort of loop. So suppose this is inside my graph, right? Here we have 4 vertices and 4 edges. And I'm going to denote by L1, L2, L3, L4. Those will be my edge labels. And as I said before, so L1 is really equal to x plus A1 squared, right? And L2 is x plus A2 squared and so on. But for simplicity, I'm just going to call it L. And so if we have some label P on this vertex, well, then this next vertex has to be of the form P plus some constant times L1, because the difference has to be a multiple of L1, and so the multiple is a C1, right? And then if you go to the next vertex, well, then we have to add a multiple of L2, so it's P plus C1 L1 plus C2 L2. Same for the next one, right? So I'm just adding a multiple of L3 But then since we are going around the loop, we also have a condition that if I take this this vertex label minus the P, that has to be a multiple of L4, right? So really what we get is we get some condition if we have a loop that the sum of the edge labels with these coefficients should be equal to 0 for given cycles. Okay, so what we are going to do now is we are sort of going to capture these conditions in a matrix, and then we're going to be interested in what is the rank of this matrix. Okay, and so one question is, so how do we sort of capture all the loops in the graph? And for a planar graph, you can look at the cycle bases. So a cycle is just a sequence of vertices such that every two adjacent vertices form an edge, right? So that would be a cycle. And then in a planar graph, if we have a planar embedding without any crossing of the edges, then we can define the faces of the graph, and each face is bounded by a cycle, so we call that a phase cycle. So here again is a very simple planar graph. I labeled the edges by E1, E2, E3, E4 up to E8. Here we have two faces, right? This face that is bounded by E1, E2, E3, E4, and then a face bounded by E4, E5, E6, E7. And then we have this extra edge that is not associated to any face. And what we are going to use is sort of, the cycle basis for this graph, which means we are actually going to use the phase cycles, so the ones that are given by the faces of the graph. Okay, so if we do that, we can associate a matrix to such a graph in the following way. So if I'm going to just order my edges in a certain way, so E1, E2 up to E, the number of edges, in this case 8, right? I just need a certain ordering to actually write down a matrix. And then I'm also going to order the bounded faces. So in this case, we have two bounded faces, right? As I said, the ones bounded by E1, E2, E3, E4, and the one bounded by E4, E5, E6, E7. Then we can form the phase cycle basis matrix by, so for every face in the graph, we will have a row in our matrix. So in this case, we have two rows. And then we have EG, so the number of edges, many columns in the matrix. And we just put a 1 in a particular row if that edge is on the face associated to this particular face. So here, since one edge 1, 2, 3, 4 are associated to face 1, we have ones in the first 4 columns, and since 4, 5, 6, 7 are the edges for phase 2, we have ones in columns 4, 5, 6, 7. And then edge 8 doesn't occur at all in the phase, so that's why that column is just equal to 0. Okay, so that's how we get this particular matrix. And well, how do we now capture the conditions that we get? Well, remember that our edges are labeled by, oh, sorry, now I label them AI, X plus Y, but it doesn't really matter where you put the constant. Okay, so we label them by AI, X plus Y squared. And then remember, for a cycle, we get a condition like this, that they have to add up to 0. So if I plug in what our polynomial is, we get this equation. But you want that the coefficient of every monomial, so x squared, xy, and y squared should be equal to 0, right? So if I expand that out, so therefore I get that the sum of the squares of these labels AI have to add up to 0, and then the the sum of just these AIs have to add up to 0, and these coefficients themselves also have to add up to 0, right? So I basically, for every cycle, because we are in degree 2, and therefore we look at coefficients of x squared, xy, and y squared, I get 3 conditions on these coefficients AI that specify my edge labels. Okay, and we can capture that in a matrix, namely basically take that phase cycle matrix that I had before, but for every row corresponded to a given phase. I'm now sort of expanding that because every phase now has 3 conditions, right? So row 1 is the 1, 1, 1, 1, 0, 0, but then the linear condition, so that the like a linear combination of the AI has to add up to 0, is captured in the second row, and then the squares of these numbers also had to add up to 0, or like linear combination of this. So that is given by sort of the third row, and then you do that for every cycle, and that gives you this extended cycle basis matrix. Okay, so those basically now capture our conditions for these coefficients. And one thing that you can relatively easily prove is, so this is not a very special theorem, but what you can prove is that the dimension of the spline, if you take out sort of the constant splines, is the number of edges minus the rank of the matrix, because so the sort of, if the rank of the matrix is maximal, then we have 3f rows now, because for every f is the number of faces, and we would have a condition, 3f conditions, right? So therefore the rank is sort of reduced, sorry, the dimension is reduced by the rank of this matrix. And why the EG? Well, think about the tree case again, right? If I take out the constant spline, then the number of edges really tells me the dimension of the spline. Right, in our very first example, we had 2 edges. If I take out the constant one, then there were 2 edges and the dimension is 2, or in our case it was 3 if we take the constant one. Okay, so basically what we are now interested in is how can we compute the rank of this matrix in an efficient way, or in a nice way, or in a combinatorial way. So the rest of the talk will be about how can we sort of analyze the rank of this matrix. Any questions so far? This would be a good point to ask a question. Okay, so then what we are going to do now is we're going to analyze the rank of this matrix, right? And you can also sort of see that if the 3 times the number, so FG is the number of faces, and EG is the number of edges in my graph. So if 3F is smaller than the number of edges, then it's sort of like a short, fat matrix. And if the matrix is full rank, then the rank would be 3F. So therefore, in this case, the dimension of the spline would be E minus 3F. If it has more faces than edges, it would be sort of a skinny, long matrix. And in that case, if the matrix is full rank, it would sort of be overdetermined. And it turns out that then usually the dimension of the spline would be equal to 0. So the more interesting case is when the number of edges is bigger than 3 times the number of faces. Okay, so that's mostly the case that we will be looking at. And yeah, so if you look back at this matrix, right, so let's say I take a 3 by 3 sort of submatrix of this, 1, 1, 1, A1, A2, A3, A1 squared, A2 squared, A3 squared. If I took the determinant of this would be exactly the Vandermonde determinant. So this is what this comment is saying, right? So if I take sort of certain 3 by 3 submatrices, I get the Vandermonde determinant. And well, to determine what the rank is, we can look at the determinant of the matrix. And one thing that I will now do is we will write down a formula for the determinant of this extended cycle basis matrix that uses these 3 by 3 Vandermonde matrices or Vandermonde determinants. Okay, and one thing that you should also notice is, so in the 3 by 3 case, right, this determinant would be non-zero if these labels are all distinct. So if AI is different from AJ and AJ is different from AK and AI is different from AK, then these differences are non-zero, so the determinant is non-zero. And this is what we call the generic case. So in general, if we look at the determinant of this matrix MX, it will be some polynomial in these variables AI. Okay, and if this polynomial in the variables AI turns out to be a non-zero polynomial, we call that the generic case. Because if that polynomial is zero in itself, then the rank is definitely smaller than the full rank. Okay, and also one thing that will actually turn out to be important is that this number 3 is actually special for these degree 2 splines. And the reason is sort of because, well, when we expanded our degree 2 polynomial, right, we looked at the coefficient of x squared, xy, and y squared. So those gave us 3 conditions. So we expanded this cycle basis matrix. And every phase sort of gave us 3 conditions. So that's why the number 3 actually turns out to be important. Okay, so one thing that we did first was we actually wrote down sort of a nice combinatorial formula for the determinant of this matrix MX. And it turns out that you can sort of view this combinatorially as something doing on the graph. So I'm going to now define what is called an edge-injective function. So curly F is just a set of all faces in our graph. And this edge-injective function will go from these faces to an unordered triple of 3 edges. And these tuples, these triples should have the property that the 3 edges should be on that face F. So we are going to associate to a particular face F 3 edges, and these should be on the boundary of the face. And we also want, so this is why it's called edge injective, we want that every edge is only associated to one face. So the image of 2 different faces, the intersection should be empty for 2 different faces. So really what you can think about is you have your graph, you have your faces, and now for a given face, I'm just going to pick 3 edges that are associated to this face. And for the next phase, I'm going to associate 3 edges that are associated to this one, such that I never pick an edge for 2 different faces. That's basically what this is saying. And then if we take any sort of 3K by 3K submatrix of MX, we can write it as a sum over these edge injective functions. And then these products are basically products over these 3 by 3 Vandermonde determinants. Okay, so this NF phi F basically means I pick that particular face that corresponded to 3 rows, and then I pick the 3 columns specified by the image of phi, and that gives me a 3 by 3 van der Monte determinant. So basically, this is a sum over edge injector functions of a product of van der Monte determinants. So that's why this formula is nice. And well, since we want to sort of understand the rank of this matrix, we've now sort of reduced it in some way to a more combinatorial problem by trying to find edge injector functions on a graph. Okay, and as I said before, so the generic, we call it the generic case when the determinant of n, which is a polynomial in these AI, it's a non-zero polynomial. So it's not zero by itself. And also, as I mentioned before, so when we have fewer edges than 3 times the number of faces, the dimension of the spline in the generic case is 0. So because in that case, the rank of the matrix would be E. And remember, the formula was E minus the rank of the matrix. So it would be E minus E. So that would be 0. And also notice that if a graph has leaves, so meaning edges that are not on a face, these edges sort of don't play any role in the conditions themselves because they're not on a face. So so they only basically come in the formula in the EG, right? So they sort of give only conditions as in the tree case. So they give like degrees of freedoms, but they don't come up in extra conditions. So therefore, from now on, I mostly assume that our graph has no leaves because the leaves are sort of easy. And so if we have a graph without leaves and no proper subgraph G prime has this condition that, and by proper subgraph, I should actually say, I'm going to pick a subset of faces, and then I'm going to look at the graph that is specified by these faces. So that's really what I mean. So if for such a subset of faces that graph G prime has a condition that EG is less or equal to 3F, so if the graph G does not have such a subset of faces, then the dimension of the spline is precisely what we would expect, namely E minus 3F. Okay, so the question is now, what happens when you have a subset of faces where the number of edges is less or equal to 3 times the number of faces? And in this case, we call the subset of faces contractible. And it turns out that if you have such a contractible subset of faces, if we actually contract those, meaning I really just view them as one vertex, then the dimension of the original graph is the same as the dimension of the splines of the graph where I contract these faces. Okay, so the dimension doesn't change. So basically, the way that we are now going to determine the dimension of the splines is by some algorithm where we successively contract these faces. And for this result, I now need to assume that our graph is finite. Planar has no holes, so like every face, there's not like an empty region that is not a face. So only the outside of the planar graph is sort of the outside, but there's no thing in the middle. And I'm also going to assume that 2 faces share at most 1 edge. Okay, this is because we do certain counting arguments that only work in these cases. And then our algorithm is, well, find a minimal contractible subset of faces, meaning by minimal, I mean there's no other subset that is smaller and where you have E is less or equal to 3F. And then once you have such a minimal subset, you contract that subgraph. Then you repeat until there's no more proper contractible subset. And then at the end of the day, for once you do that procedure, the dimension in the generic case is E minus 3f. Okay, so now after all the theory, let me give you some examples. So here's again one example that we had before, right? So we have 2 faces, we have 8 edges, so this edge, now what I'm going to show you is how this edge injective function works. So I'm going to associate 3 edges to every face. So this face here that was bounded by edge 1, 2, 3, 4, I'm now going to associate edges 1, 2, and 3 to this face. So that's why I labeled them in red. So they correspond to this face, and then I associate 4, 5, 7 to this face. Okay, and so therefore there existed an edge injective function. And remember, the determinant of our MX matrix is the sum over all edge injective functions. So that here I gave you one particular edge injective function, and basically what this is telling us is there is no subset of faces that is contractible in this case, right? Like if I take one of these faces, E is 4, F is 1, so 4 minus 3 is greater or equal to 0, so they're not contractible. So therefore, in this case, the dimension of the spline is really 8 minus 3F, so which would be 8 minus 6, which is 2. So for generic edge labels, meaning the edge labels are all distinct, in this case, the dimension of the spline is 2. So that was like an easy way of computing, like a nice combinatorial way of computing the dimension of the spline. Here's another example. Again, you can check that there are no contractible subset of faces. So, and here is again one particular edge injective function. I associate 1, 2, 3 edges 1, 2, 3 to this face, 4, 6, 7 to this face, and then 5, 8, 9 to this one. So in this case, the dimension of the degree 2 splines would be 0 in general, because I have 3 faces, 9 edges minus 3 times 3 faces, so the result is 0. And since there are no contractible subset of faces, I didn't have to do any contraction. So you can see it's relatively easy to actually compute this. And here's another example. So here is a graph where I can actually contract a subgraph, right? So here, this face here has only 2 edges. So if you compute number of edges, which is 2 minus 3 times the number of faces, so it's just one face, so 2 minus 3 is minus 1, so that is less or equal to 0. So therefore this subset, this face is contractible by itself. So if I contract that, this just means I really just contract this whole subgraph, so that becomes one vertex. And so the edges 5 and 6 disappear, and I end up with this particular graph. And then this one is not contractible. You can see it has one face, 4 edges, so 4 minus 3 is 1, so the dimension is 1. And therefore, the dimension of the original one is actually also equal to 1, because of this procedure that we can contractible subset of faces. Okay, so this gives us this algorithm of computing the dimension. Yeah, so for the last couple of minutes, what I want to do is tell you a little bit more about when do these edge injective functions exist. So we actually have a procedure, we have a nice way of constructing all of the edge injective functions for such planar graphs. And then the other question is, when do generic edge labels actually exist? And so for these results to hold, we assume that G is a finite planar graphs without leaves. So the leaves, again, they're sort of easy to handle for the dimension formula. And I'm now assuming that the graph does not contain any proper contractible subset of faces, right? Because if we did, we could sort of contract down. And then the claim is that there exists an edge injective function if E is greater or equal to 3F, just under these conditions. And then we are claiming that there exists a generic edge label, meaning that the determinant is a non-zero polynomial in these AI, if in addition to these conditions, at most two faces of G share at most one edge. Okay, so we need that in the proofs for certain counting arguments. And notice that this condition that two faces of G share at most one edge is equivalent to saying that in the dual graph, there are no multi-edges. Okay, so now let me first talk about briefly about this. The first question about constructing all possible edge injective functions of a graph. And notice here I actually do have two faces that share more than one edge. So this result holds even in that case, just the generic edge labels, there we need this extra condition. So here I have a graph, and I have actually given you a particular edge injective function, right? This face here, I have associated E1, E2, E3 to it. Here I have associated E4, E9, E10 to it, and so on. So the colors just tell you which face they correspond to. And I'm now actually going to go to the dual graph. So every face now corresponds to a vertex in the dual graph. And so an edge between two faces is now an edge between those two vertices in the dual graph. And notice that an edge that is sort of on the boundary of my graph, I'm now going to associate to loops. Okay, so this is now my dual graph to this graph. And I've also put directions on the edges, and the directions really correspond to having picked an edge injective function. So let me just walk you through this. So here phase 1, which corresponded to this, my edge injective function, right, had associated edges 1, 2, and 3 to this phase. So therefore in this dual graph, this arrow goes into my phase. Okay, and for the loops, again, the loops go into the phase because those edges were associated to this phase. And then this F3, this would be this phase, right? This E4 corresponds to this edge that now goes into F3. So the arrows, if an arrow goes into an Fi, that means that edge is associated under the edge injective function to this particular vertex. Okay, so we now have this other way of viewing our edge injective function. And now here's a way to construct all of the edge injective function for a graph. Basically what you do is you look at the faces of the bounded faces of the dual graph, but not the ones for the loops, just the proper ones. And so I have labeled them here alpha, beta, gamma. So suppose we have an edge injective function. The way that you can get all other ones is by reversing directed cycles. So for example, here we have a directed cycle around alpha. So if I reverse that, I get this down here, right? And then you can actually go from sort of any such edge injective function to any other one by reversing a particular cycle. So for example, to go from here to the one in the bottom left, I actually reversed the alpha plus beta. sort of cycle. Okay, so we have a way of constructing all possible edge-injector functions. And then to check whether we have a generic edge labeling, we had to sum over all possible edge-injector functions and check that none of the terms actually cancel, because we want to have a non-zero polynomial, right? So that's why it was important for us to actually be able to construct all edge-injector functions. And I want to say one more thing about why this condition that two faces share at most one edge, where this sort of came from. Well, because there's this nice lemma that a graph G has a minimal contractible set of faces. Well, either if G is a single face, so it's either a loop or a double edge or a triangle. And you can see that in all of these three cases, we have one face, right? In the first case, we have only one edge, so E minus 3 is minus 2. Here we have two edges, so we have 2 minus 3 is minus 1, and here we have 3 minus 3 is 0. So in all three cases, this face is contractible. But under this condition, the only way to get minimal contractible set of faces if G is a single face or this difference is equal to 0. And this helped us a lot in the proofs. So if this is not the case, then E minus 3F can actually become more negative for certain subgraphs. Okay, so let me sort of conclude with the takeaway from this talk. So we were able to compute the dimensions of splines, and there are sort of two aspects to the problem. There's a combinatorial aspect and an algebraic aspect. So the combinatorial aspect was, yeah, these edge injector functions, right? We associate three edges to every face. And the algebraic aspect was, well, do certain polynomials or determinants vanish or not? And that's more like an algebraic condition. Can we solve such an equation? And the combinatorial aspect of like associating these three edges to every face, that sort of governs the generic case when the polynomial is really non-vanishing in these AI. And the algebraic aspect determines more the non-generic case, because in that case, the polynomial is actually equal to 0. And yeah, here my collaborators. We started this project during the pandemic, so most of our stuff was done by Zoom, but actually recently we met at MSI in Berkeley, and we made a lot of progress on the problem. So thank you very much.
Well, for the triangulations, right?
Sorry, can you repeat?
This probably works really well for the triangulations of the objects, right? When all the faces are triangles.
Mm-hmm.
You said this was a case that was often considered when you're actually working with some surface?
So I think the original sort of question about this upper bound conjecture was done for triangulations, but that would really be in the dual. In our setting, it would be the dual graph. So the dual graph would be a triangulation. Yeah. So I guess in our case, it would mean that the degrees of the vertices are 3, but we didn't really need to use that in our analysis.
That probably applies really well to that case, right? Because both faces share just one edge. And